Hi, everyone. This is for week 3, the activity on gene expression data and TCGA clinical data. So let me get out of what I'm doing here, clean everything up, go into our folder, which is Dream High 2026, and the week 3 activity, which is the R Dream High TCGA expression heat maps. Now we don't need our console, so that can always be minimized. So for me, I'm going to restart and clear the output just so that no one, we don't see it ahead of time before we run it. Okay, so as usual, the first thing we want to do is save the file as another name. I want to make it clear that if you append to the file name, it should occur before the file extension. If we add something to the file extension, it becomes a completely different file, and R won't recognize it, and we'll get some goofiness. Okay. And people have been forgetting to put their names here. That's a dead giveaway about an activity. And you should put the date in, however you like, with Thomas, of course. Okay. So this is a nice activity because we're going to take what we learned about heat maps and what we learned about the patients from the TCGA 1082 cohort breast cancer patients and their gene expression data. And we're going to work with both sets of data, clinical data and gene expression data separately. But then when we integrate them, we're going to find something exciting about the biology. So our learning goals are to load a gene expression matrix, which we've done for you. We've created that. We've done the so-called data wrangling. We want you to understand what the rows and columns mean, to explain why selecting a smaller set of genes for heat maps is a reasonable approximation. We'll talk a little bit about log transformation and scaling. And we're going to add clinical labels to the heat map. This will be pretty exciting, I think. So our data directory is set up. We're going to read in the expression data. We're using read RDS because we have the data in internal format to R. It just makes it easier to store large files. So you see it's 160 megabytes. It's a pretty big file. And as usual, we should be getting used to these commands, dimensions, and also doing subsetting of a matrix to see what's there. If we look at these values, we see that they're pretty tame. It's likely that these were already log transformed. And don't forget to answer the questions and also the reflections as you do these activities. Remember, we're not asking you to do any coding, but we do want you to understand what you're doing, and answering the questions and reflections is critically important when you're doing this work. So the values in the expression matrix are mostly between 0 and about 21. Let's check that. So we're getting a summary, the median and the mean, and the maximum is about 21. So there's a little reflection there for you. All right, the clinical data, let's load that. Okay, you remember this, right? There's patient barcodes, and there's all kinds of features about the patients. Now remember, let's see, here for the expression data, the patients are actually the columns. You should have written that here, and the genes are the rows. But when we did the clinical data, we worked with it such that the patients were the rows. So we're going to have to be careful about that as we move forward. And previously in the clinical data activity, we used the table command to get summaries. So for the estrogen receptor status, we found there were about 50 that were unknown or missing, and we had many more positives than negatives. All right, so this is a very important step, is making sure that the samples in the clinical data set and the expression data set are aligned. So what we're doing here is we're taking sample IDs. Those are the columns, right? The columns from the expression data, and we want to map those with the breast cancer patient barcode from the breast cancer clinical data frame, which happen to be the rows. So match is whether you give it two vectors and it matches the elements across the two vectors. And then we want to sum how many are not available. If we're lucky, we'll get 0. So that means we have 0 cases in which we have NAs. So that means all of them match. Another way to look at it is in this code chunk. I'm not going to discuss it, except it tells us the same thing. All right, so for each gene, we can calculate its average expression across all tumors. So that means across the column, I mean the row. So we're going to apply the mean across each row. That's what one means. If we put 2 here, we would be getting means down the columns. So let's see what we get there. Okay, we have a little median that's a little higher than the mean. They're numbers. This is a bit of a long code chunk, but it's nice. It gives a little bar plot. Okay, so we have a median here at 8, a mean at 6.85, and then a minimum of 0, a maximum of 16.5. So we discussed here that this is likely to be gene already log transformed, and you'll learn a little bit about what skewness means. Like, what does it mean that the mean and the median aren't the same in a sample distribution? Okay, so let's look at a histogram of this mean gene expression across breast tumors. So each value is the mean expression level of a given gene across patients. And you see that there's some bell curve or normal distribution character here. All of our statistics in R require or assume that we're working with normal distributions or bell curve distributions. We have this business here at the end in this tail, but based on what we know from experience, this is a very good um, normal distribution. We don't see this very often, so we're going to move forward. And this is what it means that data is dirty or tricky to deal with. So we have to sometimes take what we get. So here's a reflection for you. And we talked about reduction of dimensionality when we met last time. We want to see if we can do that here. We want to take fewer samples, and we're making a hypothesis that the genes that have the largest variance, meaning that they change the most across patients, carry more information. So if you had a gene whose value was the same across all patients, that's not a very informative gene. But if you have a gene whose expression changes across patients, especially when it changes coordinately, from luminal A to luminal B, so on and so forth, we would expect that that gene would be highly informational. So we're going to use the apply on the rows to get the variance of all the genes and look at that summary. Okay, so we have a median and mean of variance and a maximum of 27. It doesn't really mean all that much to me. Let's take a look at the histogram. All right, so what this is showing us is that most of the genes have a very low variance. Like, most of them have a variance of very close to 0. So we're interested in the genes that have higher variance, and there's not that many of them. So we're really going to dramatically reduce what we're looking at to about 100 genes. Okay, that sounds like a lot. So we're going to order our genes according to the variance. Decreasing equals true, means that we're going to start at the top, the highest values, and order downward. And then we're going to take the top 100. So the expression for variance at the very top are those from, once we've ordered it, 1 to 100. Okay, so now we have 100 genes, the most variable genes, but we still have 1,082 patients. So we're just doing this randomly. We're going to choose every fourth sample. We have way too many patients for this many genes, so we're going to take a sequence from 1 to the number of patients we have by every 4. Okay, so we're going to grab from that every fourth sample. So now the dimensions of our sub-expression matrix is 100 genes by 271 patients, so 100 rows and 271 columns. Okay, so now the most important heat map correction that we have learned is scaling, and for expression matrices, scaling, we scale the genes, not the samples. And you can read about that here. So we have to do a little bit of a transposition here in order to get it done correctly. Again, I'll let you read that. And this is our distribution. Thankfully, when we scale things, we should have a mean of 0 and a median or a standard deviation of plus or minus 1. And that's pretty close. The third quarter and the fourth quarter are pretty close to plus and minus 1. So we're very used to doing heat maps. So we've created this object called, where did you go? Yeah, here we are. The expression subscaled. And that's what we're going to be making our heat map of. The smaller expression matrix that has 100 genes and 271 patients. So we've done heat maps before. This allows us to choose what colors we want, and we're going to use the typical red, white, and blue. So heat colors here comes in down here for the argument color. Okay, look at that. It's beautiful. We do see some patterns in here. This is definitely a pattern. Here's another pattern. And this could be a pattern here, and I would say there's 4 patterns, because here we have a lot of red at top. All right, so there's some reflections here for you. And now we're going to add the estrogen receptor status. So to make it easy on us, we're going to use a plus sign for estrogen receptor positive patients, and just a dot rather than a minus sign for the estrogen receptor negative patients. So estrogen receptor status is from the subclinical matrix, the estrogen receptor status, right? We know now. So with the data frame, if we start typing in the name, it gives it to us. So we're going to replace every positive with a plus sign and every negative with a dot. And then we're going to look at a table of our labels. All right, so we have mostly positive samples, and we have 13 samples with nothing associated with them. And you guys correctly identified these as missing data. Okay, so now let's make a heat map using these annotations, the plus and minus signs. So we'll run that code. We get the same heat map back, but now we're annotating it with plus signs for cases where the tumors are estrogen receptor positive, and dots where it's ER negative. All right, so there's some more questions for you to answer. And then we look at something here called a marker gene heat map, where we're just going to look at a set of what we call biologically meaningful genes, and look at their gene expression. And we pick these by hand from the literature, we know that they're important. And here, each of them is explained. This MKI67 is a proliferation marker, and that is why luminal B is more aggressive than luminal A, even though both have ER plus, PR plus status. There's more MKI67 in luminal B, and it makes the cells grow more quickly. So we have our set of marker genes, and let's take a look at those. We've made a list, and now we're going to make a heat map of a subset of our submatrix for just this set of genes. So you'll see that it's a very small heat map. And it's interesting to see that, and we've also put the estrogen receptor status for the tumors here. So let's look at ER positive. So we have a lot of MKI blue, which means it's more lowly expressed. And up here where it tends to be estrogen receptor negative, it's more highly expressed. Interestingly, this is the progestogen receptor. Well, let's look at the estrogen receptor. For all of these positive ER positive, this is our sanity check that yes, indeed, estrogen is more highly expressed. Where estrogen receptor status is negative, it's more lowly expressed. And we see this echoed also for the progestogen receptor. Okay, so some more questions for you to answer. Now we're going to do the same thing for the progestogen receptor that we did for the estrogen receptor. We're going to use plus for PR plus and a dot for PR minus. So we run that heat map. Oops, I forgot to run this code to create the labels. It's always nice to make a mistake, right? You get seized in your heart and then you realize, oh, all right, I can fix this. So now we can run that and get the heat map. And we see something very similar that we saw with the the ER status. A lot of positive samples and then a group of negative samples. So I guess I answered your question here. Do they look similar? So now our second challenge question is the HER2 status. So let's give labels to HER2 positive and negative. And interestingly, look how many values we have that are indeterminate or missing. It's a lot. So we have to take that into account. We're going to be missing that data in our labeled heat map. So just as we did before with PR positive and negative and ER positive and negative, we're doing HER2 positive. We have a few here, and most of them tend to be negative where the data exists. So does it separate as clearly as the ER status? Well, obviously not. So you should answer these questions. So finally, we're doing triple negative breast cancer. This is where we have negative status for all three receptors. So we're creating a special label when all of the statuses are negative. We're going to call it triple negative. And we're going to have a label for that. So we have 27 cases of triple negative and 244 of undetermined. So we're finally going to do one more heat map, and we're going to annotate it with the triple negative breast cancer samples. And it's really amazing that the only ones that show up are associated with this first pattern, where we see a lot of overexpressed genes and a lot of underexpressed genes. And those patients are associated with triple negative breast cancer. So the point to make here is that we've looked at two completely different data sets, right? Information on the patients that were collected in basically the doctor's office in the clinic and doing histologies and following up on treatments. And here we're just looking at the levels of expression of their genes. And we're able to make a correspondence between receptor status and also triple negative breast cancer. This was transformative in cancer biology when it was first done about 15 years ago. So this type of analysis is still done today, but I want you to really appreciate that this is an association. It doesn't necessarily mean that it's causative, but we have been able to make this correspondence without manipulating it. It just fell out of our analysis. So there are some more questions and some final reflections. You should save your file, then knit it, and once you have it knit, it should pop up. Takes a while because there's a lot of large data sets. Okay, now I can publish it. I can publish it to RPubs. Always publish to RPubs. Okay. So I can add some details and then I would get a URL associated with this that I could put on my website. Okay, so that's it for this week's activity. And I'll end the video now.